There we go. So I'll be looking. I think some of what I'm talking about has already been discussed. But we're looking at the populations of these orbitals and distribution over space and time. So last week we did the red pill sensor calculations. This week we're looking at the dynamics. I followed along using the MATLAB code. I also, like a couple other people, had some issues running my own examples. So if there's time, I'd appreciate any feedback on your it too. But for this model, I did the same model that is the Ligma Q was working on. So as also has been mentioned, an application of looking how these populations change in space and time can help you see how the charge transfer goes around. So in the MATLAB script, there's 3 big variables that help look at the populations and how they change over time. So one's is PPE, as it's called in the script. It's a list of the population electron states at some position at some time. This in the script ends up depending on your HOMO and your max occupation level. There's this PE, that's an spatial distribution of the electrons, and this comes out of your band out file. And then WPE, it's a product of these 2 variables, which are matrices. And this ends up helping us analyze how the orbitals change over time. So I have another slide here to show like how this would look in equation form. So here we have our PPE, our PE, which ends up being densities. I guess it's covered up on Zoom here, but there's a picture of like what it looks like in the code and line it's on. So once MATLAB has that, if you look at waterfall plots, this is just generating the command line what these all individually look like. So the first one's just this population, the second one is densities. The third one is just third one's initial like kind of like a skewed view of it, and then if you just were to do a top-down view, that's this right panel. This ends up being related to plots we can see later, but MATLAB processes further before we get there. So after you have your WPE, for the final visualization of the graphs that MATLAB automatically generates if everything's working, it normalizes WPE, it extracts some electron data, then extracts hole data, and then it plots the data individually as electron holes or both electron and holes. So here is just the electron hole graph. Again, you see it's similar to the raw WPE data from before. So this shows position on one axis, time over the other. Some general interpretation about what's going on here. This contour, or since this is a contour plot, you can, in MATLAB, there's a tool you can use to look at color bar on the side. The brighter values in this case correspond to electrons. The darker values, or the negative values in this case, correspond to hole locations. If it's neutral color, what I understand that means that whatever was there in that place, the charge, or it didn't really, the charge density matched what it was before, so there wasn't really a transition. And this is the way you can see that over time, that charges move. So I guess in the case of this example, we have charges that end up focused more over here versus in these different positions. So that's all I have for this presentation. I'll leave it up for questions on this.
Okay, please join the second presenter. Any questions in the audience? Any questions online?
Just one question with the graph we got up right now. How could you relate it to like the HOMO levels, or like where you excite your electrons, where you put your holes? Or is there any way of like being able to tell that from this graph, I guess?
That's a good question.
I will make a comment wearing a hat of a mathematician. The answer does exist.
Yeah. I guess my guess would be here you have various bands. But my guess would be each of these would be like an energy level for the electrons, like, and then maybe a more luma would have to be individually checked out between each of these lines.
Okay. So, any additional interpretation? Okay, this question and this answer is one of the rare examples when realistic systems in the nature agree with our intuitive expectations about the models. So, if you temporarily stop sharing, I'll start sharing and make a little demonstration. So this is the data set from CARE, and the initial conditions for the example that was used as by everyone who tried. The electron initially is promoted from luma to luma plus 1, and hole is promoted from HOMO to HOMO minus 1. So both luma and HOMO, both occupied and unoccupied progression of orbitals, satisfy the intuitive expectations for the particle in the box concept. So if you look on the luma, the blue image here, so it has less density at the edges, more density in the middle. Second, luma plus 1 has less at the edges, more in about water from the edges, and less in the middle. So it shows this understanding that it is not a continuous particle in the box, but electron can stay only on the ions. So it's discretized representation of the particle in the box. And the illustration that was demonstrated is when one creates initial excitation of electron in the luma plus 1, where the density is in these two humps. And as time goes by, it relaxes and solidifies into the center. So we see how particle in the box concept experiences relaxation from first excited to the ground state for electrons, and similar pattern for holes. Thank you, Joseph. Thank you. Great question. I'll stop sharing. Hadassah, would you please share, and maybe there will be more questions?
Okay, so Dimitri asks third last slide, panel 1, top left.
Well, it's not sort of sports, like slide number 5 is counted for frequency.
Please describe or interpret the image. We'll be able to obtain the same result by pen and paper without a computer. So, this represents our population of the orbitals. I think this this axis here corresponds to the band number, or
Just number of orbitals.
number of orbitals.
Okay.
And there's only 2 shown here. So, I mean, I could.
So another axis is timeline, right?
Yeah.
With time steps. So keep analyzing, because we all need to do it later for our practical research.
It kind of reminds me of the energy levels where you can see like a HOMO LUMO. Well, that.
So it's luma plus 1 and luma, right? if it is for PB or electrons. Okay, keep going.
So you can, I guess it's showing Luma plus one relaxes, I guess you can see the exchange of the electrons or the electron population over time. So you go trades off between energy levels.
Uh-huh. Okay. And second part of the question.
Could you say the same result gave for the computer? I guess practically on the mathematical side, only so many electrons can be occupied on all the levels.
Like, can you get the same or similar lines without a computer? Like what do you need? Which equations you need to solve and how the solutions will look like?
I'm just thinking of things that could put you share electrons between energy levels.
So this system of equations. So rho and one each. Let's name it as a unit, like Luma plus one equation is losing its occupation proportionally to its original occupation. So we can just use variables that we like better. So dy dt equals minus constant 1. So how will you solve it and what is the solution?
Integration. No. Or integration over time.
And what will be the answer? You don't need even pen and paper, you just solve it in the air.
It's just equal to the rate.
So what's the solution for y over time? Julia? Would you like to go and solve?
Yeah, I think so.
Okay, please.
So it's yes,
Y. No. Y is I disagree with your second. Okay.
Y squared by 2. Y squared by 2. The other side and then yes.
don't we just have dy here?
What? Should you transfer y on the same side?
Oh, yeah.
So
Yeah.
all unknown function on one side, all independent function on the other.
Forgot about
Okay. Oh, much better. Yes. Great. Okay, and how to make it y equals something? What should you do to the left and right part? Perfect. Thank you. Everyone agrees? Hadassah, does it make sense?
Yeah.
Do you have any maybe confusion or disagreement? Because this solution is by you look exponentially decaying, and here it looks more like going in a theta function. So, do you have any confusion or disagreement with how it looks there and how it is seen here? No? Or do not hesitate.
Okay, No, I was misreading dy dt and y was variable percentage.
So the images that we all are plotting with this code use time and logarithmic scale, and then this exponential decay looks more like a theta function. So just a trick to compress more time steps in a shorter window. But if you have only two levels, you don't need computer. We just take this R element of vertical tensor from initial calculations and just solve it by independent way. So we need all this computerized technique only if you have like a lot of levels. Okay. More questions to Hadassah? More questions 1? More questions 2? More questions 3? Many thanks.